Very good. Okay, thank you very much. My name is Marco. I'm from Tobias Kippemer Lab, but I'm going to start my own group in Sherbrooke in a couple of months. So if you're interested to do a PhD, just let me know. The motivation, we just saw the nice talk before, and we all know how to make a qubit. So we just take a substrate that is mainly for mechanical support. We make a sheet of some metal, superconductor, aluminum, for example, and we want to control this qubit. So we will have some waveguide that controls it. This is the ideal case. In practice, we have thermal photon in the waveguide, we have TLS on the substrate, we have quasi-particle, as we just saw before, and we have phonons. And this is what I want to talk about. And normally you will say, okay, these phonons will just make your qubit decohere or lose energy faster. But a couple of years ago, we showed that if you measure, sorry, I'll just take the laser pointer. If you measure repeatedly the readout of the, it's okay. Now there is the laser pointer on the screen. If you just measure population, you will see that while you expect just certain random quantum jump, you can see that the population of the qubit just gets excited very repeatedly. And now if you put some accelerometer on top of the fridge, you will see that this excitation really correlates with the pulse tube shock. And even more, if you just turn off your pulse tube, your qubit goes quiet. And this is very bad news, because now if you have two qubits, as we made on the chip, both can get excited at the same time, and this can cause correlated errors. And people are, in fact, also aware of this, and there are many strategies already for isolating superconducting qubit from phonons. We can see that a transmon, it will increase its lifetime when it crosses the phononic bands. In a phononic crystal, the TLS made on phononic crystal will increase the lifetime themselves. We saw that the quasi-particle have different dynamics with the pulse tube on and pulse tube off if they are isolated mechanically. So indeed, all the paths that I showed before are important and coupled to the mechanics. So our approach is a little bit different. We want to make a density modulated phononic shield that we will wafer bond on some support, mechanical supported substrate. And this, we believe, has some advantage, especially in the qubit fabrication process. So you can see now that the exposed surface of your wafer is basically indistinguishable of a normal wafer, silicon wafer. So you can do all harsh cleaning process when you fabricate your qubit. And also during the release part, you will only access the back of your substrate. So you will completely not touch the qubit. So we want to show this process that, of course, is a bit more complicated than just 3 steps. So first, we need to be able to make the density modulated phononic shield. We need to be able to bond this on a wafer, and then indeed release a very thin silicon membrane. So we start from this. We pattern the bottom of the wafer, and we etch with the sequence of dry etch, xenon difluoride, and HF vapor release. And we're able to indeed release, I hope you can see, a relatively large area of a thin single crystal, 200 nanometer thin silicon membrane, and on a very large scale. Now, since you can see on the SEM, it means that there is some topography. Indeed, if you now use some profilometer, you can see that you get every 500 micrometer, 5 micron buckling up. This means that it's indeed close to the fracturing point, but so that's the maximum you can suspend. Now we want to make qubit on it, and as you know, when you make a standard qubit on fully supported structure, you will have the electric constant of your silicon that will help in making relatively large capacitance. We shoot for 100 femtofarad more or less. But now if you have suspended the element, either you make a very dense capacitor with with interdigitate capacitor, or you need very large area. So since we can maximally suspend 500 micron, this trench edge is indeed 500 by 500 micron, our Trasmon will have a shape that look like this. So now the gap here is around 10 micron. That should still give very high coherence, but nevertheless, we decided to not go for this route. We switched to fluxonium. So now we still want to be dielectric limited. So we still want to have a relatively large capacitance for the fluxonium, and but this should allow to still have much smaller dimension of the suspended structure. And an additional point is that going through the fluxonium, we can reduce the operating point without needing huge frequency point, without needing huge capacitance. So we can shoot for frequency of the qubit around 1 gigahertz. So in this case, we designed this density modulated membrane where you have 250 nanometer thin membrane and pillars that are around 500 micrometer high, and this will open band gap around 2 and even 1 gigahertz. And these are band gap, phononic band gap stays even if you evaporated aluminum on top. So for this we can use optical lithography. So you can see it's 1.2 micron wide the diameter of the pillar, around 400 or 300 nanometer the separation, and we have the luck to have deep UV. Basically, with a big mask like this on 6-inch mask, quartz mask for the UV, we are able to pattern the full 4-inch wafer in like 10 minutes. Then there is the bonding. So we are able to make the phononic shield. About the bonding, we use this bonding technique where you activated both surface and you just place one wafer on top of each other. And this wafer bonding will apply some pressure in the vacuum and temperature, and that's how effective the two wafers are bonded. To assess the bonding of the two wafers, we use this infrared transmission. Here you can see that except very small area, the bond is almost perfect, and on the edge of the full wafer, this white area is just the part where the optical lithography effectively leave space for the wafer. So we're able to make the phononic crystal, we're able to bond the wafer, we're able to suspend the structure. The only thing that we need to be able to make is a fluxonium, and we have this the only piece that are missing for making fluxonium from a Trasmon is the Josephson junction array. So effectively, we made this 4-angle, if you want, evaporation, where first, as you see in order, first we evaporate 20 nanometer of aluminum to, without breaking vacuum, 40 nanometer. Then we oxidize the aluminum, and then we do 60 and 120 nanometer of aluminum. We design a chip like this with a control Trasmon and 2 fluxonium. And when we realize it looks something like this. And you can see a zoom of the Josephson junction array in this part. So we have only preliminary measure of the fluxonium, but more or less from some calculation we are able to extract the parameter of the charging, that is around 1 gigahertz, what we wanted, energy, inductive, and the Josephson junction energy. And the lifetime of this fluxonium, that I remind you, this is non-suspended, this is just a fluxonium on normal silicon, are also quite decent. So in the next step, indeed, we are designing a fluxonium that is suspended on the silicon membrane that is phononically shielded, as I showed before. But you can see that now this is only 150 or 200 micrometer by 200 micrometer release gap when you need to release it. So in the following step, indeed, we'll realize the design that I show. We will release it, and hopefully we will see some enhancement in the lifetime, or if we make multiple fluxonium, no correlated error. With this, I just want to invite you to the other talk from the group. So there are many of them. And of course, this wasn't only my work, it was the work of many people, as you can see here. And the final slide, since I'm leaving the group, if you're interested to go and substitute me, please write Tobias. Thank you.
All right, question?
What is the dissipation mechanisms for the phonons, do you think? Clearly there's something